presenting our study, check risk prediction via multi-objective hyperparameter, optimization, balancing, macro F1, and business uplift. Bounce check prediction matters because a single bounce check causes a heavy losses to a financial institute. And currently there are rule-based systems that do not get all the coverage from the data. And if we implement, artificial intelligence, machine learning models, we can use all the data available and use everything at our hands to check if whether or not these checks are safe or not. And also manual reviews can lead to risk checks and wrongly reject the safe checks also. And our approach is to implement machine learning based binary classification models, and we'll be separating our models into two segments, two customer types. We will be optimizing the models with more than one metric, not a single metric. And we also have an out of time holdout evaluation, which are the last 3 months. Segment specific modeling. Modeling is that we have separated our dataset into two types of customers, individual and corporate customers. And we have done this in order to capture their distinct risk patterns and their decision thresholds. We also have multi-objective optimization, where we balance macro F1 with a business uplift metric, where we calculated with profit and loss rates, avoided loss minus missed profit. We also threshold tune each segment on the validation sets to optimize them. And finally, we have an out of time evaluation, where we compare the models on the last 3 months of the dataset they have never seen. Our dataset consists of 951,000 rows with originally 77 columns, but currently we have around 200 features. The difference will be explained later in the presentation. In the individual segment, we have a bounce rate of 3.15%, and in the corporate segment, the bounce rate is 5.27%, which is because it's an imbalanced class of datasets. Before data splitting, we preserve the last 3 months of the dataset as an evaluation set. And then on the remaining dataset, we split it into 3 parts: train, validation, and test, where train has 70% of the dataset, validation and test has 15% each of the remaining dataset after the 3-month holdout. And we also implement pre-processing and we implement feature engineering to the dataset. In this sector, removing rows were not acceptable. Therefore, we used all the missing value strategies we can to ready all the rows for model testing. And we also scaled the models specifically for segments. And there's also an inflation normalization on the transaction amounts, which is a very important column to level the playing field when on all check data from 2022 to 2024. We implemented various feature engineerings ranging from ratios, subtractions of dates, etc., to time-based features. For example, one being the performance of the check givers on 30-day base slots. And we also handle the segments differently. The reason why there are different amount of features is because we implemented cluster-based feature engineering, which had varying optimal K values for each segment. That's the reason. We compared 6 model types for a comprehensive evaluation, which are these models are LightGBM, XGBoost, CatBoost, Random Forest, X-Trees, and Logistic Regression, which acted as a baseline. We selected LightGBM and XGBoost as our primary models. They have the best performance. CatBoost model also has the best performance, but during the development phase, CatBoost training was a bit costly. It took more time compared to the others, vastly amount of different time. Therefore, we focused on LightGBM and XGBoost most of the time. And here's our approach to multi-objective optimization. The main objective is the macro F1 score, and the second objective is business uplift. And we do this by running, for example, 50 Optuna trials, where we record both metrics. Then we find the trial with the maximum F1 score. Then we remove our threshold from it, the tolerance value, and we select all trials in that range. And then we pick the one with the highest business uplift. And also we tune the probability threshold on that specific model hyperparameters on our validation sets afterwards. With this, we achieve multi-objective optimization, where we are not constrained to a single macro F1 score. We also include business-related decisions to this process. As you can see here, we have another metric, gross sunk rate, which is the amount of bounce checks, transaction amounts total predicted safe, divided to the total amount of predicted safe checks. Lower is better in this metric. It measures undetected risk exposure. Previously, this metric was included in the optimization directly, but we removed it because it encouraged overflagging, where it flagged a lot of safe checks as risky, which in turn lowered the gross sunk rate, but resulted in a lot of missed profits. Here we see the two main models results, individual and corporate segments. As you can see, in individual, it scored around 87%, and in corporate, 89%. The gross sunk rates are vastly lower than the datasets original values, which are around 3 and 5%, and here we have around 1 to 2%. And lastly, importantly, we compared the model's result in the last 3 months, where we calculate the profit. In the all safe scenario, we accept all the checks in the last 3 months, and we compare the profits to that. And here we can see that in the individual, we have around 1 to 2% profit increase, but in corporate, we have a significant increase around more than 30%. And here we see all the models, and we can clearly see that in the individual side, random forest, XO3s, and logistic regression performed worse compared to the top 3. But when we look at the corporate side, we can see that they all had an increased profit, but the top 3 models achieved more than them. Segment-specific modeling matters because when we looked at the results, they had different results values, different F1 macros, varying results in the profit comparisons, etc., which kind of supported our idea that there are distinct risk patterns. We also had a multi-objective advantage. We didn't solely rely on F1 macro score, where we could have missed some significant financial gains. We also implemented gross sunk rate as a monitoring metric, but we later removed it from the optimization process because it encouraged overflagging, as I've mentioned before. And there is also, we have to say that there are some limitations to this study because our current data set consists of only accepted checks from financial institutes. It doesn't include all checks that were proposed to the companies. Those checks were hard-coded rule systems, remove those checks entirely without thinking anything. We don't have those values because they were not given to us, which introduces a certain bias, of course. Also, our profit and loss rates are fixed, which may not reflect the real world conditions. And there's also the risk of customer behavior drift. In time, some things might change, and also significant world events might also change the model's performance as well. To conclude, the segment-aware, utility-driven model selection improved both the prediction quality and the financial outcomes, as we have seen. Light GBM model was selected as the best model when considering the balance. It had higher scores in both individual and corporate segments. We also had the multi-objective optimization advantage to our advantage. In future work, we aim on creating more hierarchical clustering features, more TSNA-based feature enrichment. We will also be searching for alternative search methods such as genetic algorithms, which we are currently working on. We will also have to implement drift monitoring and threshold updates when we deploy these models. And we also have to search for alternatives to undersampling for class imbalance. Thank you for your time. You can contact us through these email addresses.